Okay, so this is our last video about topological concepts, about the chapter on topological concepts in the notes, where, as I said, you can study this from so many sources. In some sense, it really doesn't matter which one you pick. Okay, we're going to be talking about induced topology. I left over this thing here from our previous videos saying that we have all these equivalent conditions for continuity as long as I have a function between two metric spaces x and y. So, but I need to remind you that we define continuity by saying what about if I have an f function from a subset of x, y? I mean, I'm not going to write it down, but x and y, okay, this has metric d sub x, this has metric d sub y. Maybe I did write it down. Okay, and sorry, I'm going to move this a little bit. Okay, good. What is the problem with this? Well, one makes sense as long as I restrict my sequences to be contained in D, and I have X to D in D here, and that's actually our original definition of continuity. It was like that. You have a domain that's a subset of X, and that's how you do things. 4 also makes sense if I only consider points in D here. However, 2 and 3 right now do not make sense. Well, they actually do, but so I need to put D here, but I need to make clear what I mean, right? So the point is that I'm really not talking about the same topology as before, right? So before I had that X was the whole set. So if I needed to replace things here by D. And what does it mean to say that a subset of D is closed? Well, if you want to use this theorem the way we wrote it, you need to talk about G with this induced metric by D sub x. Right, the induced metric is just, well, D sub x measures distances in x. D is a subset of x. Therefore, I can measure distances in D. And this gives me the same thing over here, right? Now, remember our general definition of a topology related to a metric space. So this is a metric space, right? D with induced metric. I'm assuming that D is an empty if you care. And what is this? So it's a collection of subsets of D such that A is open according to D sub D. So it's a collection of sets that are open according to the induced metric. And what I want to talk about is what these sets look like. And I mean both open and closed sets. Proposition 1 is that a set A belongs to this topology, therefore it's open. And if and only if there exists another set that I'm going to call A tilde contained X open in X with A equals A tilde intersection D. So we're going to show that now. What is this saying? Okay. In principle, we don't know much about these sets. We just say, well, I give you a metric, right? So you define open sets according to that metric. So what is that? And I mean, but here's another way to see these guys. Okay, so open sets of D with induced metric are open sets of X intersected with D, right? And this has some funny consequences if you think about it, right? And perhaps the hardest thing about this topic is understanding these consequences. Uh, so say you have here the real numbers are x and the rationals are d. And I have, say, the open interval from -1 over 1 intersected with d, with q, right? So -1, 1 is intersection q, is open in q, but not in R. How is that? Well, I'm assuming the proposition, right? So -1, 1, the open interval is an open set of R. Therefore, its intersection with Q is an open set of Q. It's an open set in the topology of Q with the induced metric. But this is clearly not an open set in R, right? So if you take any ball around a point in the set, well, it has to have a rational center, but as a subset of the real line, right? So this thing is full of holes, right? So there's no way to find open balls inside this guy. Open balls according to R. The funny thing is that they're open balls according to Q. And when we prove the theorem, we're going to notice why that is, right? So here's the thing. The reason why we have these funny phenomena is that balls in this space are kind of funny. So we're going to use a result that says that a subset of D is open in D if and only if it's a union of open balls and these are balls in D, right? So this is going to give one direction, which says that if A is an open subset of D with this topology, then it has this form. Okay, what are these balls? Okay, right? So what's a ball in D? Well, it's the set of all points in D at distance less than delta from X. No big deal. Now, this is the induced metric, right? So when I measure distances between points in D, by definition, this is the same thing as measuring distances between points in X, except that the 2 points lie in D. Now, look at this. This is almost the open ball around X in the space X, right? So what is the open ball in X? So it's a collection of all X prime in X, whose distance is less than delta to X. Okay, so this is almost, but not quite, right? So this is exactly if you think about it, it's the open ball. So, okay, it's almost this, right? All points in the space X, they're within distance delta from the center. But now I want to restrict further. I need to only take points in D. So here's what's being said. An open ball in D with the induced metric is simply an open ball in X that you intersect with D. And how is this useful for us? Well, basically it says everything, right? A set A is open in D if it's a union of open balls in D. And that's if it's a union of open balls in D, then it's a union of open balls in X intersected with D. Now what? The union of those open balls in X is precisely the set A tilde that I'm looking for. So, okay, here's what I'm saying. In order to construct an open set in D, what you need to take is a bunch of open balls in D and unite them. Another thing you can do is you can take a bunch of open balls in D, take their union, and then intersect with D, right? So I'm using the fact that union and intersections are commutative in the sense. It doesn't depend which order I do them. But now, again, so process number 2 is saying take a bunch of open balls in X of this form, right, with centers in D. And So if you take a union of open balls in X with centers in D, that's an open set in X. If you intersect that with D, it's an open set in D, in the space D. So that says that any set of this form is a union of balls in X, that's a tilde, intersected with D. Well, there's a converse statement which is showing that if this is true, this is true. This is really trivial. It's just a matter of saying, okay, if a point's in here, then it has a protective bubble in X, and this protective bubble intersected with D is a protective bubble in D. So I'm not going to prove the converse statement. I mean, in some sense, I haven't even proven any direction. That's mostly a thing that I want you to think about, because it's, in terms of proof, it's not hard, but it's counterintuitive. Okay. But here's a corollary of this that I want to discuss. Okay, there's a proposition 2, which I'm going to write now here, which is really the same thing. And again, I'm going to leave it as sort of an exercise. It's just about taking complements, right? So I'm going to sketch it quickly, but again, it's not hard. It's just that you have to wrap your head around it. You have to get used to this. So a subset of D is closed according to tau D metric if and only if there exists a closed subset of the larger space such that f is equal to f tilde intersection D. And the proof of this more or less is follows. So f is closed in D if and only if its complement is open. We know how to characterize open sets, or the intersection of open sets in the larger space with D. And then you just play around with complements and you're going to get this. So this f tilde in some sense is the complement of a tilde that I had before. Okay, all of these things, they're actually instances of a more general thing. So, which I'm going to add as a remark here. Right, so there's a general construction where you take a topological space and you take a subset of it and you define a topology of that subset. And that topology is called the induced topology. So let me write this general thing here. So I'm kind of temporarily back to this realm of general topological spaces. Remark. Given X tau topological space and a subset of X that's non-empty, the induced topology, which is just a collection of all sets of the form open. Well, okay, so take all of the open sets of X, intersect them with D. This is a definition of the induced topology. Well, it's a little bit of an exercise to show that this is indeed a topology on D. For instance, how do you know that the empty set is here? Well, the empty set is here. It's a section with D is the empty set. How do you know that D is in here? Well, X is an open set of the space X. X intersection D is D, so D is in here. It's closed by unions. I mean, just playing around with these little things that we saw before. So this is indeed a topology. This is induced topology over D, right? So given a subset of D, I have an induced topology of it. And what we've shown is that in the metric setting, that is when T tau, right? So when tau is given by a metric, tau d, the induced topology, is given by the induced metric. So if you look at it in terms of playing with words, it's not at all surprising, right? So I have a concept of an induced metric. I have a concept of induced topology. And what I'm saying is that when the original topology is given by a metric, the induced topology is given by the induced metric. So this is sounds a little bit funny. It sounds even trivial. It's not entirely trivial. It's exactly the propositions that we proved before. What we proved before was that the open sets of D with induced metric were all of this form. They were open sets of X intersected with D. So there's a theorem there, a proposition if you like. It's not entirely obvious that the induced topology and the induced metric coincide in some sense, but they do. And now I want to prove one last fact about induced topologies, and I mean, it's actually a fact about, about general topologies. Which I'm going to write down here. If D is open in X, then open subsets of D are also open in X. A similar statement holds when D is closed. So if D is closed, then closed subsets of D are also closed in X. Okay, why is this non-trivial, right? So notice that I'm talking about two different topologies here. I'm talking about tau of D, and now, I'm saying that D is open according to the topology on X, right? So let me call this tau of X, just to make clear. So D is a member of tau of X, and what I'm saying here is that members of tau of D, elements of tau of D, right, open subsets of D, are also open in X. How does one prove that? Well, okay, one direction is easy. Notice that the open sets of tau of D, sorry, it's not one direction that's easy. So both directions are easy. In fact, so let me add something here. In fact, in this case, right, so tau of D is the collection of subsets of D that are open in X. So this is what I meant to say. I meant to say that if D is an open subset of X, then the topology induced over D consists precisely of those open subsets of X that are contained in D. Okay, how is that, right? So first of all, if D is open, look, all of the sets in the topology tau of D, they're open, right? They're the intersection of an open set of tau and tau, right? An open set of X, this is tau of X. Here I have the intersection of an open set of X with D, which you're assuming is also open in X. The intersection of two open sets is open. Therefore, these guys are all open subsets of X. So tau of D consists entirely of open subsets of X that are contained in D, because, well, when you take this intersection, you have a subset of D. Now, any subset of D that's open in X is also open in D, because A intersection D is an open subset of D, but A intersection D in this case is equal to A. So what I claim is that, okay, these guys are always open subsets of D and open subsets of X. On the other hand, any open subset of D has this form, and therefore this guy is a set A in tau X, because we notice the intersection of two open sets in X. And therefore, and so open subsets of X that's contained in D. So in fact, all the sets in the topology are of this form. Open subsets of X contained in D, and all sets of this form are in the topology. So again, let me confess, as a teacher, as an instructor, it's a bit hard to explain these things because they're almost tautological. I mean, I think you're better off trying to check learning sort of the facts from me and trying to check or do the proofs by yourselves. It's all set theory, elementary set theory. It doesn't mean it's easy, but you need to try it on yourself. So what I'm saying is that, okay, if D is itself open in X, then open subsets of D are open subsets of X. In fact, all open subsets of D are open subsets of X that happen to be contained in D. These are all. And the same thing if I have closed, then I'd say closed subsets of D, also closed in X. The closed subsets of D correspond to the closed subsets of X. They're contained in D. Okay, this was a bit quick, but hopefully it makes sense. Okay, so that's sort of useful sometimes because sometimes we'll prove that certain subsets of a certain D, say, are open in D, but we want to know that they're open in X as well. So, okay, how does this relate to what it started from, which is just saying a continuity, right? So, as I said, if you want to define a continuous function over D, you need to use the induced metric. That gives the induced topology in this sense, right? I argued that the induced metric gives you the induced topology. So when you define continuity in these topological forms, you can use the induced topology with no problem, right? So let me just emphasize, if I write things like this, I mean a closed subset of Y has a preimage, which is a closed subset of D in the induced topology, or sometimes called relatively closed. And this is also in the induced. So this fills a bit of a gap, which is, we know before we had talked about continuous functions for the whole of X to Y. Now we have continuous functions over the subset of X to Y. And all we need to do is to use the induced metric or equivalently the induced topology. The point of this video is that the topology induced by the induced metric is the induced topology. And that's it. That is the end of this week on topology and continuity. We're going to continue with topological concepts and the relationship to continuous functions over the next few weeks, maybe, or the next 2 weeks. Thanks.